Welcome back, chemistry fans. Today we are going to try and practice the rate law expression topic that you just learned about in class. We've got two quick problems, but they're intense. They've got a lot of details in them. They're not mathematically challenging, but there's a lot of details that we need to sort through. So let's see if we can make headway through this together. I'll go very slow, and hopefully you will feel like you are prepared if we or when we have some questions on these next class as a little quick quiz. All right, so these are the two questions that you have. The first one is dealing with writing out a rate law expression. Now, what that means is you write the word rate because that's what we're looking for in this one. We're trying to figure out what is the rate if I have these as my new amounts in this reaction. We're trying to predict how fast it's going to go if I put those amounts into that equation. Well, I haven't got an equation, so we've got to write the equation for it. So the rate is going to be equal to some constant, which we'll calculate eventually, times the starting material times the other starting material. Now, normally, whenever we did equilibrium, the coefficients became the exponents, but we don't know what the influence is until we do an actual experiment with it. And they tell us what the influence is here. Those are the initial rates once I plugged in these values here. So we're going to use those and figure out if, in fact, those coefficients are correct in the reaction. So here we go. Let's now do a little bit of math. It's not challenging. So what we're going to need to look at is let's compare trials 1 and 2 and see who caused the rate to change. Notice it started at 0.8, now it's at 1.6. Well, what caused that? It is not because of NO. Because if you look at NO, it's the same amount. Well, if I use the same amount, I shouldn't see a change in the rate. But what did change is the bromine. So mathematically, here's what we're going to do. We're going to take the bigger number over the smaller number. So we're going to put 2 divided by 1. And then we're going to say that that is equal to some exponent x. We're going to use that x up here. Oops, sorry. We're going to use it over on BR. But over here, we're going to figure out, well, what is that exponent? So we're going to take, again, the bigger number divided by the smaller number. So let's simplify. So now I've got 2 to the x is equal to 2. Well, what number would that x be equal to? Well, it'd be equal to 1. That x would be equal to 1. So that's what my value is for that order associated with BR2. So now let's do the same math principle. Let's set up the same type of exponential ratio type thing for trials 2 and 3. Now notice BR did not change in trials 2 and 3. What did change is the NO doubled, but we still got a change in the rate. So now again, I'm going to set up another little expression here. So I'm going to say 2 over 1, the big over the small, equal to, and this time I'm just going to use a z so that it's a different value. So this time I'll put a z so that you don't think that they're going to be the same. So it could be any letter. Over on the right side, my initial rates are 6.4 and 1.6. So now I'm going to simplify. So I've got 2 to the z is equal to 4. Well, what would the number for z be that would make it equal to 4? So it'd be 2 times 2 is equal to 4. So that tells me what this z is in my rate expression. Boom. Good job. Okay, now we have our rate law expression. The only thing that we are missing is this constant K. It is the same for every reaction at a given temperature. All of these are held at the same temperature. So we are going to now be able to plug in either 1, 2, or 3 into this rate law expression to solve for K. It does not matter which I choose, so I'm going to make it simple. I'm going to plug in rate law, or I'm going to plug in trial 1. So I'm going to substitute this data for there. I'm going to substitute this data for here. So I have rate is equal to 0.8. This is my rate, is equal to K times 1 squared times 1 to the 1. Well, that's pretty easy, right? Because 1 squared is 1 and 1 to the 1 is 1. So my K is going to be equal to 0.8. Now I can substitute this in. Now I have my complete rate law expression. The final step in this problem, number 1, is that we plug in these datas that were given to us. These 2 points were given to us. So now we're going to plug those into the equation, and we will be able to say what the new rate is based on the information that we have. So my rate is equal to 0.8 times 0.6 squared times 0.4. So let's plug that into a calculator. 0.6 squared times 0.4 times 0.8. And my rate is going to be equal to 0.1152. 0.1152. That is my new rate. So this is the final answer that we are looking for on number 1. Quite a bit of detail involved in that. Let's jump down now and talk about the Arrhenius equation and plug in some data and see if we can solve for the K value if we didn't have all this rate law data that we are given on number 1. Is one of 2 things. It could be either K is equal to, if we're looking for the rate constant, A, which is a equation constant. It's a second constant. It's the Arrhenius constant of this one, multiplied by the exponential to the power of negative EA over RT. And that's really, really mathematically challenging. So it might be easier, and it will be easier for us to write this in the following manner. The log, the natural log of the rate constant is equal to negative EA divided by RT times natural log of A. So if we get to that point, we're going to more easily be able to solve for what we're looking for in just a second. And that's a plus out here. Okay. So here we go. Let's start substituting values in and solve for what we're looking for is the activation energy here. So we have a rate constant of 1.35 times 10 to the negative 4, and this is natural log of that value, equals negative EA, which is what we're searching for, divided by the R value, which is 8.314, that's a constant given to you, times the temperature, which is 308 Kelvin, plus the natural log of another A. This is the same A that was in the first equation. This is a second constant. This is the Arrhenius constant, 4.79 times 10 to the 13. All right, let's plug all these in. First off, I'm going to plug in these natural log values, and then I will try and combine them all together. So natural log on your calculator is not the same as log. It's ln. So you may have to do a little bit of searching to find that value on there. Negative 4, whoops, negative 4, 1.35. Negative 4. And that's going to be negative 8.91 equals negative EA. So that's where those negatives are going to cancel out here in just a second. 8.314 times 308 is equal to 2,560.712 plus now the natural log, again, weird button. You're going to have to search for it on your calculator because it's not intuitive as to you want to use the regular log. This is natural log. It's a different mathematical function, 31.5. Okay, now what we can do is first things first, algebra says you have to move this 31.5 to the other side first off. So negative 31.5 to the other side. So now plus 8.91, and we have 40.41 equals negative EA over 2560.712. So now we've got a cross multiplication. This is going to end up being a very large value. So 40.41 times 2560.712, very large value. Oh, and that's still negative, by the way. So I've got 103478.4 negative equals negative EA. All we got to do is make those positives and we have our answer. All right, so the activation energy, this is in kilojoules. That makes more sense now if we think about this one. Or this is probably in joules, actually. This is probably in joules. And then we can divide it by 1,000 to make it into kilojoules. All right, so it makes it a lot more sensical that we have this value here in heat values and not some weird random other exponential value. So if we were to turn this into kilojoules, 1, 2, 3, we'd have 103 kilojoules. Not that much. Okay, this is everything that I wish to share with you today about rate laws. We'll have a couple of problems dealing with this on a quiz that we will take on our next class. Thank you so much. Talk to you again soon. Farewell. Bye.